Now that Melissa read that long title, my 10 minutes may be up here, but so you can see the team there, and this work is a collaboration between the University of Central Florida and the University of Notre Dame. And so I'll give a brief outline here, and I always like to start out with, motivation. Why do we care about the work? And so then I'll go through methods regarding cone penetrometer testing, and I'll use CPT hereafter in the talk. Then I'll talk about the Ryder Terra Mechanics testbed, and then I'll give an overview of the GATOR project. And I might have to rethink this name. I went to the University of Tennessee. I'm a volunteer, so I don't know what I was thinking there. But then I'll go over some GATOR project CPT results for a Viper-like lunar rover wheel. And we were instructed by Glenn Research Center, which nicely lent us that wheel, to call it a Viper-like. We weren't allowed to call it a Viper wheel. And then if I have time, I'll give a plug for our two facilities at Exolift Lab, Ryder and Crater. And so there we go. So long duration stays on the lunar surface will require investigation into the trafficability of the lunar surface. And by trafficability, I mean the capacity of a soil to support a vehicle and provide sufficient traction for movement. And on the image there, road construction on the moon, I put a question mark because this hasn't quite been worked out yet. How do we most efficiently get around on the moon? Is it necessary to build roads? If so, how do we stabilize them? Or is it efficient to drive over the same tracks between point A and point B if you're making continuous traverses? Or will it be like Back to the Future?
Roads? Where we're going, we don't need roads.
For example, like lunar flying vehicles or lunar hoppers. But in the near term, we're going to be driving around on wheels. So anyways, the work is relevant. And so, most of our team are geologists. We're interested in rock, soils, minerals, that sort of thing. We're not trying to build a better rover or design a wheel. And so thinking about trafficability from a geological perspective, we thought, what happens to the soil after long duration repeated traverses over lunar soil in the vehicle? And we thought that this required and was an important topic for investigation now that we're going back to the moon. And so here's some methods. And so cone penetrometer testing, we used a RIMIC CP40 cone penetrometer, and you can see it there in the cartoon, the green instrument there. And this is based on the physics of wedge penetration through a dense soil. And on the left there, you can see one of our two-layer tests using LHS-1 Highland simulant in our plexiglass bins, where we replicated the stratigraphy as measured in situ at the Apollo 16 landing region. And so if you look at the plot there with the colored graphs, that's our raw data for CPT insertions into LHS-1 simulant that was packed at 1.71 grams per centimeter cubed. And so we use these curves to drive the G-slope, which is simply the slope of the stress over depth curves there. And so what can we do with these data? And if you look at the plot on the left, we can actually derive a strong correlation between the G-slope parameter and bulk density of the regolith, or the regolith simulant in this case. And so that's that plot on the left is 45 insertions. So that's 5 different insertions at 9 different density packings to derive that correlation. And so you can see it's a strong exponential relationship there. On the right, this was one of our two-layer tests that was conducted to try to replicate the stratigraphy as measured at Apollo 16. And so the blue curve there shows our laboratory curve, and the black curve is that laboratory curve with a correction factor of 0.29 applied to correct for lunar conditions. And you can see that matches the profile as measured by cone penetrometry during Apollo 16 stations 4 and 10, and those are the gray curves there. And so we successfully replicated the stratigraphic profile, the top several decimeters of the lunar surface at the Highlands region of Apollo 16. Now, how is our Ryder Terra Mechanics testbed interesting and versatile? Let me count the ways. But unfortunately, I don't have time to really go over our rig here at Exolith Lab. But what I will say is look at the, you can see some of the features there in the bullets at the bottom there. And then I want to point out that Ryder is available for contract work to the planetary science and engineering community. So what's up next? The GATOR project overview. So we made a two-layer regolith column using 2 metric tons of LHS-1E engineering grade simulant in the Ryder testbed. So that 2-layer test I showed you earlier, we scaled up significantly in the Ryder test bin. And so we tested 3 lunar prototype wheels, and you can see them in the picture there, the Viper-like resource prospector wheels in the middle. And we performed, you can see the compaction method we used, the vibration compaction method to create the layers. And so we tested the 3 wheels, and I'm going to show you the results for the Viper-like wheel, where we did 900 total passes per wheel, pausing every 100 passes to sample the geotechnical properties. And you can see that list, the geotech properties listed there in the table at the bottom. We're still working on reduction and interpretation of particle shape, data, and particle size distributions. But today I'm going to show you some of the cone penetrometer results for the Viper wheel. All right, let's move on to, there is the Viper-like wheel in action on the simulated lunar surface there in the Ryder bin. And if you look to the lower left there, you can see a map view drawn to scale of the test bed. And so you can see the track there plotted. But I want to point out that the baseline CPT insertions are in the red asterisks. And that, by baseline, I mean before any wheel passes. The in-track CPT insertions are performed after every 100 passes in duplicate, working in from the ends of the bin in blue. And then the orange hexagons there are outside track CPT insertions using the same pattern. So let's move on. And so here's some of the results. And oh yeah, and keep that color scheme in mind. Blue for the in-track, orange for the outside track, and red for the baseline. I'll use that in the next couple plots here. So inside track, G slopes increase for, I only got 10 slides left. It'll be fine, yeah. G slopes increase for both the upper layer, which are the blue crosses, and you can see the horizontal red lines there for the baseline values, and also for the lower layer. And for the outside track, you can see that for the orange crosses, they're relatively unaffected. They're down there near the baseline values, but you can see that there is an increase for the lower layer, which are the orange hexagons. And an interesting behavior that we noticed in these data is that you see how the maximum G slope, which correlates with compaction and density, like I explained earlier, is reached at about 600 to 700 passes. And we hadn't kind of expected that it would plateau or it would keep increasing. So this is unusual behavior. And I'll talk about it a little bit more on the next slide, where again, red baseline, and I'm not showing all 900 passes here for clarity, it would clutter up this plot, but I'm showing 300, 600, 900 penetration resistance curves, penetration depth over stress. And you can see that for the inside track, again, upper layer and outer layer show an increase there for compaction and increase in density. But the lower layer, outside track, is very similar to the baseline for the upper layer. It's not affected, but the lower layer is affected. And I've overlaid these. I'm going to flip them back and forth so you can kind of get the sense for the data. Inside track, outside track. Okay, and so that increase for the lower layer in the outside track can be explained by this passive pressure theory from civil engineering, where this is a cross-section of the Ryder bin looking down the length or the direction of wheel travel. And you can see the affected regolith underneath and the outside track CPT insertion. And this is based on the, you can see that angle, and the angle of psi there is the angle of internal friction. And so that explains that lower layer increase. And I will move on to summarize here where what I told you about the inside track and outside track data are kind of expected and intuitive, but the point is that these effects can be quantified in test beds on Earth in preparation for lunar exploration, construction, trafficability. And so then I already told you the unexpected result was that bottom one there where we reached a max at about 600, 700 passes, and then it seemed to relax or fall off for some unknown reason that warrants further investigation. So thanks a bunch for your time. I didn't get a chance to promote our facility as an Exolith, but I've got old school flyers at the registration desk if you.
We can discuss that at the end. Thank you.
Yeah, thanks.